We are a new section, and just to throw the cat amongst the pigeons, we're not doing today 2.4. We're jumping straight into 2.5, which actually is not a problem. There's nothing in 2.4 that you need to know to be able to do 2.5. The reason I'm jumping by 2.4 is I don't like 2.4. 2.4 is like a lawyer got involved in mathematics. It's called the formal definition of a limit. It really doesn't bring anything to the party. It's a piece of knowledge that we kind of formally have to do, because we have to say, well, at least you've seen the background to these things called limits. But in a practical sense, they're not that useful. So I'm skipping it right now because it interferes with the flow. And then once we've finished 2.5, I'll then go back and do it. And when we do it, it's going to be a little bit different than any other section that we'll do in this quarter. We're going to do all the homework questions together. So when you get to see it, I'll be doing, I think there's 6 questions. I'll be doing all 6 questions with you. So hopefully you've got your own website up and running, or at least got a copy of it. Okay, so what's section 2.5? We are going to deal with a concept called continuity. So a function is said to be continuous at some point x equals a if this is true, that the overall limit as x tends to a of the function is the same thing as the value of the function. So that's it. A function is continuous at some point x equals a if the overall limit is the value of the function. And a function is not continuous. A lot of textbooks, including WebAssign, uses the word discontinuous. So a function y equals f of x is discontinuous at a point x equals a if one or more of the following are true. If the overall limit does not exist, it's discontinuous. If the limit is plus or minus infinity, or f of a, I should say, the value of the function is plus or minus infinity. If the overall limit is plus or minus infinity, they will use the word not finite, but it means the same as this. Or if the overall limit is not equal to the value of the function. So these are the main types of situations where a function is not continuous, and this is the one and only situation where it is. So if this is true, it's continuous. If this is not true, then one or more of these were the reason. Right? Put that over here. So there are 3 common types of discontinuity. If you ever see a graph where there's a hole like this, and maybe the value of the function's up there, maybe that dot is not there, but the key feature is that there's a hole there. This is called a removable discontinuity, and this one fails under number 4. Right, the overall limit exists, but it's not equal to f of a, either because f of a is up there or because f of a does not exist. Right, so now you might say, well, does it fail under number 1? Is it a discontinuous because 1? Well, the overall limit of this function does exist, right? The overall limit is whatever the height of that hole is. So the overall limit in this picture does exist. It fails because the overall limit is not equal to the value of the function. So we call these removable. I think they get that name because if I pick this little dot up and put it there, you'd be able to remove the discontinuity. It would end up being nice and smooth. Now, the second kind of discontinuity is called a jump discontinuity. And this is an example of one where the left branch and the right branch do not meet up, right? There's a distinct gap. And you see that little solid dot means the value of the function's there, and the little open dot means that the value of the function is undefined. These two could both be little circles. That one could be a dot, and this could be a circle as it is here, but you could switch places. You could even have 2 circles and the dot up there. They all count as the same thing. There are all examples of jump discontinuities. And this one fails because of number one, the overall limit doesn't exist. That's correct, because it's got a left and a right limit, but no overall. And it fails also because of 4, because the overall limit doesn't exist, so it's not going to be equal to that either. And then we have the third kind, which is called an infinite discontinuity, and we would think of them as vertical asymptotes. So x equals a, there's a vertical asymptote, and it fails under number 1 because the overall limit does not exist, meaning it has to be a number to exist, and it's not. It fails under number 2 because the value of the function is either plus or minus infinity, which it could be clearly be. Fails under that. And it fails under the fact that the limit is also infinite. So we are looking altogether at 3 major types of discontinuity. These are the ones you're going to see most often, pretty much all the time, with a few minor exceptions. So when I look at a graph and I'm looking for where is it discontinuous, where is it discontinuous, the way I kind of do it is a little pretend story. Pretend the graph is a road and that you're driving from left to right. If you get killed, it's got a discontinuity, and the place that you get killed is where it is. I'll show you what that means. I'm driving along here and I get killed because I fall in a hole. I'm driving along here and I get killed because the road's broke. I'm driving along here because I get killed because you shoot me up into space and I lose all my air. Right? Can you see you can get killed in 3 different ways? Right? So that's just a little nonsense thing, but it helps me, right? So when you look at a graph, if you are traveling from left to right, like it was a road, would I get killed or have an accident? And if you say, yes, I would, you have got a discontinuity. And the place where that crash or death would happen is the x coordinate of it, at least, is where the discontinuity is. Any questions so far? We're kind of clear on what a discontinuity looks like, because continuity is easy, isn't continuity just a nice smooth curve and nothing's going on, right? Discontinuity, something's broken somewhere. Now, the last thing we're going to look at is that what we've dealt with right now is, for want of a better word, overall continuity, right? Now we're going to look at subgroup of continuity. You can be continuous from the right at x equals a. You can be continuous from the left at x equals a, or you can be continuous at x equals a. So let's look at the first one. First one is, how can a function, or what do we mean when we say that a function is continuous from the right? Obviously, a single point at x equals a. Let me show you what it looks like. We call that a right branch, and we call this a left branch. And let's say that there is x equals a, right? That's where x equals a is. This is right continuous at x equals a. And the reason for that, or one way of describing it, is the limit as x tends to a plus, right? The right-hand limit of this function is equal to the value of the function at a. So if the right branch has a solid dot on it, it's right continuous. That's all it means. Now, if you go for the second situation, piecewise functions are very often going to be right and or left continuous. Now, if you do the second situation, which I should have put its name down and I forgot to, so I'll put it here. If you talk about a function that's continuous from the left at x equals a, there's a, then we would be talking about a function where kind of that would happen, right? Can you see that the left branch has a little dot on it? So if the right branch has got a dot on it, it's right continuous. If the left branch has a solid dot on it, it is left continuous. And we already know what an overall continuous looks like, which is that. So if you just say a function is continuous at x equals a, you would mean something like this. Can you see how continuous at a basically means it's just part of the curve, isn't it? There's nothing special. Like the left and the range, the left and the right branch meet at the same place. So mathematically, a left continuous would have this property. The limit as x tends to a minus, that's a left limit, we call that, is the value of the function at a. And an overall continuous, which is this one, would just be the overall limit of f of x equals f of a. So, right continuous, left continuous, and continuous. Do you see what the three situations look like if you saw a graph of them? Right continuous, the right branch has a dot on it. Left continuous, the left branch has a dot on it, and just continuous. We don't have phrase like left discontinuous or discontinuous at the left, and we don't have a phrase discontinuous at the right. It's not useful. So these are continuous on the right, continuous on the left, and overall continuous. So I hope you've had a chance, those people who like to take notes, to take the notes that we've got there. Any questions before we actually start looking at it? It's going to be a very visual stuff today. A lot of pictures, a lot of graphs. Any questions? You feel comfortable, you know what continuous is and discontinuous? You feel comfortable, you know what a left and right continuous looks like, what an overall continuous looks like. Any questions? Okay. Let's cut to the chase then and show you some work. You got to look at these as being very visual, as I've said before. So, don't know what that is, but go away. Okay. Are you looking at a graph with lots of broken bits to it? I don't know how best to describe it. Is that what you're seeing right now, or am I in the wrong place? I see nodes. Right, so I'll make this a little bit bigger. Is that so that matters? Yeah. Yeah. Can you see it says tutorial exercise at the top? You've got to remember what you see isn't always what I see. Okay, we're good. So what we're going to be doing, what we're going to be doing here is answering questions about continuity or things being discontinuous. So use this graph, so there's a lot of bits going on, to determine the x value. So we only want to know what the x coordinate is of this function. And we're only interested in when it's discontinuous. So let's look at that first. Discontinuous. Would you agree that the function is discontinuous at x equals -4? Can anybody remember what name we give to that kind of discontinuity? There was three names, three common ones. What do you call that one where there's a little hole?
It doesn't fall under removable, right?
It does. It falls. Yeah, it does fall under removable. Now, you might say, well, where's that little black dot? You don't need to have a little black dot, you know, a value of the function. You only need to have the whole. And when you do a removable, the two branches meet or try and meet, but somebody stuck a hole in the middle, right? Now, if you do my little analogy, if I'm driving along, won't I get killed because I fall down that hole, right? So I know there's a discontinuity there. What kind of discontinuity? That was called a removable one, right? Right, there's another discontinuity, x equals 2. Let's suppose I survived that. If I drove a little bit further, wouldn't I get killed here because I'd fall? What is happening at x equals -2? What kind of discontinuity is x equals -2? Remember, there were three kinds. Remove. Yes, it's called a jump, right? So there's removable, there's a jump, and there's an infinite discontinuity, right? That's the three most likely ones you're going to come across. Removable, which is x equals -4 as an example. A jump discontinuity, that makes sense, isn't it? A little jump, you know, to get from one to the other. Jump discontinuity. And there's an infinite discontinuity, like a vertical asymptote. Right, so I travel along a little bit further. Would you agree that there's a problem at x equals 2? What kind of discontinuity is happening at x equals 2?
Jump.
That's a jump. Now, we could argue about 4, and I think there's two answers to 4, but they don't ask you to tell what kind, so I guess I get away with it. Could you say that at 4 there's probably a jump discontinuity? Might be one way to describe it. I'm assuming that this bit on the left-hand side goes vertically downwards, because in a way, then, couldn't you describe this at least as partly infinite discontinuity and partly a jump discontinuity? It's a little bit like a Frankenstein, right? It's a bit of one and it's a bit of the other, and they stuck it together, right? But nonetheless, isn't there a discontinuity x equals 4? So when you hit tutorial exercise, which I'm not going to, but when you hit it, you're going to be able to tell me x equals, they'll give you the opportunity to do that. Now, once that's finished, we then go and we find the ax values, and we decide whether the function is continuous from the right, is it continuous from the left, or is it neither? So let's return to each of these situations, right? Each of these discontinuities, and look to see if they're left continuous, right continuous, or neither, right? That's essentially what I've got. I'm going to skip -4 for a minute. If you look at -2, is that left or right continuous? At x equals -2, left continuous or right continuous? What are you looking at?
Left continuous.
Agreed. If you look just at that part of the world, forget the rest of the graph, at this little isolated part, right, this bit here, would you agree the left branch has a dot on it? Left branch, left continuous. Okay, let's move on to the next jump discontinuity. At x equals 2, left continuous or right continuous? At x equals 2, left continuous or right continuous?
Right continuous.
Right.
Agreed. So let's focus in. I know that, you know, try and focus like a laser on that little bit near to x equal 2. Forget what's going on to the side, it'll distract the heck out of you, right? Just at x equals 2. Can you see coming in from the left, it's got a little circle, but coming in from the right, it's got a dot, right? And the guy that's got the dot is what kind of continuity you've got. Isn't this right branch got the dot in it, so it's right continuous? Okay, there's one more like this. What is happening at x equals 4? Right continuous or left continuous?
Right continuous.
Agreed. Are you all comfortable with left and right when you see it? Don't you tend to get left and or right continuous when there's some kind of jump discontinuity going on, right? There's a bit up here and a bit up here, and maybe one of them's got the dot and maybe one hasn't. Now, I'm going to leave that picture for a second and show you a situation that they didn't put there, but it can happen. I want you to imagine that I have a jump discontinuity, but it looks like that. And let's say that's x equals 3. that shape doesn't have left or right continuous. Do you see that neither of them have the point? Isn't the point right in the middle somewhere? That would have, that there then, that would just be a neither. It's neither left nor it's right. Now you could get a kind of variation on this one. Can't you sometimes get it that the function doesn't even have a dot anywhere, like in this second example? Isn't that also just another example of neither? It's not left continuous, there's no dot there. It's not right continuous, there's no dot there. Right. So that is another example of a neither. Now, one last one in that bunch that we need to do. I kind of was holding off on it a minute. Right. At x equals -4. Left continuous, right continuous, or neither. That's your choices. What's happening at x equals -4?
Neither.
It's neither. I don't know if this is going to help or make it even worse, but here we go. Okay. 1, 2, there. I'm trying to make it so there's no more graph to get in the way. I guess there's always going to be a bit of graph. Right. Anyway, can you focus at -4 a little bit better when there's less to see? Right. Do you see that if you come in from the left-hand side or you come in from the right-hand side, they both meet, don't they? But where they meet, there's not a dot, isn't there? A little open circle. So it's not right continuous, because if you come in from the right, doesn't it finish with a circle? And if you come in from the left, it also finishes with a circle. So it's neither. It's neither. It's not fish nor fowl. Are we comfortable with that then? So if someone gives you a messed up picture like this, can you find the x coordinates of its discontinuity? Would you say, yeah, I think I could do that? Could you tell me whether it was a removable discontinuity, a jump discontinuity, or an infinite discontinuity? Are you comfortable with those terms and you know what they look like? Now, lastly, could you look at that graph and say it's left continuous at x equals 2, or it's right continuous at x equals 2, or that it's neither of them at x equals 2? So you're comfortable about what a left continuous and a right continuous looks like. That's what we've done. So if you feel good with that, I'm good as well. Right, so guess what? Let's just do some practice. Practice makes perfect. Right, there's another graph. Tell me the x coordinate of any place where there's a discontinuity. I can see 1, 2, I can see 4. So give me any of them.
1.
X equals 1. Agreed. What kind of discontinuity is happening at x equals 1?
Neither.
Oh, for left and right, agreed. What name do we call that kind of discontinuity as well? Bit up here, bit up here.
Removable.
Mm,
All right.
not removable at x equals 1. Anyone else? What name do you call that discontinuity?
The jump.
Called a jump. I like the names. To me, when I see that, I can see if I wanted to go from here to here, wouldn't I have to jump? So I'm trying to remember it, right? Okay, so there is a discontinuity at x equals 1. It doesn't have a right or a left, so you were correct to say it has neither. And we would call that particular type of discontinuity a jump discontinuity. Okay, what's happening at x equals -2? That is a discontinuity. What kind of name do we give to the discontinuity at x equals -2? What do we call that kind of discontinuity?
Removable.
Correct. And because it is removable, isn't it guaranteed to be a neither, right? A neither means it's not going to be right continuous and it's not going to be left continuous. Okay, x equals -1. What do we call that discontinuity?
Infinite.
Yes, it's an infinite. You probably call it a vertical asymptote, which by the way it is, right? Infinite discontinuities are vertical asymptotes, but they're using this name, infinite discontinuity, so we better kind of get used to it. If you're in infinite discontinuity, can I just tell you right now, you're neither. You're never going to have a right or a left. Because if you're infinite, where can the solid dot go, right? It doesn't exist, doesn't it? Just keep going forever because there is no end. So an infinite discontinuity is guaranteed to be an either, right? And so is a removable discontinuity. It's guaranteed to be an either. What's the only discontinuity that I've not done then? We did one at -2, we did one at x equals -1, and we did one at x equals 1. Where's the only place where we haven't done it yet? There's one more discontinuity.
0.
Yeah. What's the name we give to it?
Jump.
Okay. Is x equals 0 right continuous or left continuous or neither? I see your mouth moving, Lizzie. Izzy, what did you just say for the benefit of the others?
I said left.
You are correct to say left, isn't she? Everyone, she's correct. It's left. Right. See why you need practice? Because the first time you're all nodding and say, yeah, I've got it. But the minute I showed you another one, you're thinking, I wonder what you call that shape again. Or I wonder if it's left. Or I'm not sure if I found all 4 of them or so on. So, you know, the time you do 5 or 6 of these, you'll get really good. There's a little baby one. Let's do my questions and then we'll do theirs. So my question is, can you tell me any place where there's a discontinuity? Give me the x coordinate of any place where there's a discontinuity in that shape.
X equals 3.
And what's going on at x equals 3? What name do we call that particular shape?
Removal.
Right? Does x equals 3 have left, right, or neither as far as the continuities go? At x equals 3, is it left continuous, right continuous, or neither?
Neither.
In fact, every removable discontinuity is a neither, right? So the minute you know it's removable, you can just go straight into neither. Right, what's happening at x equals 1? What do we call that?
A jump. Discontinuity.
Okay, agreed. Has it got left, or right continuous, or neither?
Right continuous.
Right. You see the right-hand side branches, the dot in it. We're getting better every time you see one of these, isn't it? The more experience you get to see them, the more comfortable you are at talking in the language of continuity. Now, let's look at their questions. I might have to shrink this a little. At what numbers A does this not exist? Well, when does the overall limit not exist is not the same thing as discontinuity. I'll give you an example. At x equals 1, would you agree the overall limit does not exist? Because the left limit would be here and the right limit would be here. So x equals 1 is correct. Now, the other place where there's a discontinuity was x equals 3. Now, does the overall limit exist? Yes. The overall limit is the value that the function's trying to become. It doesn't need to make it, right? There can be a hole there and it's still got an overall limit. There can even be a dot somewhere else and it can still have an overall limit. So that's the only place in this diagram, at least, where the overall limit does not exist. Okay. Let me go back to these guys. For instance, there is no overall limit at x equals 0, right? There is no overall limit at x tends to 1. So if you did a limit as x tends to 0, that's what I mean when I say overall limit, right? Does not exist. Would you agree the left answer and the right answer are different? And jump discontinuities are classic examples of no overall limit. On the other hand, would you agree that there was a discontinuity x equals -2, but doesn't the overall limit still exist? So removable discontinuities, right, are discontinuous, but don't they still have an overall limit that exists, right? So a lot of people think that overall limit and discontinuity are just different things for the same thing, right? Different names for the same thing, but they're not, right? Overall limit is not necessarily going to match a discontinuity, right? You can have an overall limit and still be discontinuous. Right, back to this fella. At what numbers for what numbers A is f not continuous? Well, that becomes 1 and 3. Put a little comma. At what numbers does the overall limit exist, but it's not continuous? So the overall limit exists at x equals 3, but it's still not continuous at 3. So that's quite a good question. Can you see how you can have the overall limit doesn't exist, the overall limit does exist, but both of those situations can still be not continuous. Not continuous, just the other word for discontinuous. Sometimes they use one, I guess. Sometimes they choose to use the other. Are we good? Right. Here's a graph with quite a few problems. In fact, it's quite a good graph. I wish it would stop putting messages. When you do WebAssign, do these annoying banners appear? Is there any bloody way of stopping them? God, that would be annoying. I mean, I get distracted dead easily, and nothing's more distracting than I'm thinking and I blink. Do they come a lot, or do you just get like one or an hour or something?
Every time you submit an assignment, like, so like if I did question number 3 and I hit submit, it would pop up last saved all the time.
Oh, that's annoying. That would drive me crazy. Is there an options? I mean, I get different version. I keep saying this, but I do. Is there an options thing in WebAssign where you can go in and change the font size or change the color or change, you know, the kind of place where you can do stuff? Is there an
Oh,
options?
I never get those. I've been using WebAssign for like 3 quarters and I haven't really got them.
And you're not getting those annoying banners?
No, not really.
Good grief,
kinda
that's even weirder. Well, if you've got the time, you know, you lot go hunting for options and see if there's an option to, I don't know what I'd call it, like disable banners or something, right?
Yeah, sure.
One of those check marks. Maybe you just had got yours like the first 2 days and you didn't even realize you'd done it. I don't know. Anyway, now I'll try and undistract myself. I kind of like this picture because basically doesn't it have everything that could go wrong? It's got an example of all of them, right? So let me do it a different way. For what value of x do we have a removable discontinuity? Where in that diagram is there a removable discontinuity? Agreed. Agreed at 3. Now, if I went and said to you, what's the overall limit? You'd say, yes, it exists. If I said to you, does the value of the function at 3 exist, right? Does f of 3 exist? The answer is yes, right? That's that little dot. If I said, what's the limit? You know, it's whatever that y value is. You could do all those things. If I said, is it left continuous, right continuous, or neither? Wouldn't you just automatically say neither? Because all removable discontinuities are neither, right? They don't have the other. Right, where in this picture, what x value, do you get a jump discontinuity?
X equals 5.
Agreed. Is it x equals 5? Is it right continuous, left continuous, or neither? At x equals 5.
Left continuous.
Left continuous. Izzy just doesn't want to tell me. She just mouths it but never says it. Okay, x equals 1. Would you agree that's an infinite discontinuity? And that means it's got neither, right? It's neither left or right. But it does have a value of the function. And that's a bit weird, but isn't the value of the function 1, whatever that dot there, whatever height that dot is at? So f of 1 does exist. So that's my questions. Let's see what theirs are. At what numbers, A, does the overall limit not exist? Now, there are 3 places we're going to be looking. At 1, at 3, and at 5. Let's start at 5. Would you agree the overall limit does not exist there? Because the left limit is this branch and the right limit's that, and they're quite clearly different. So even although it might be back to front, I'm putting 5 in. Now, let's look at x equals 3 here. Does an overall limit for x equals, as x tends to 3 exist? Stop doing that. Coming in, right? Is the overall limit. I'll take a node then, yeah? Nodes work. Overall limit works. So far, so good. Now, at x equals 1, does an overall, and the word is important here, limit. Does an overall limit exist as x tends to 1? Now you should be shaking your head. No. You could say, well, but it's infinite. And I know that is true, it is plus infinity, but its overall limit doesn't exist because we want it to be a number, right? It has to be 42 or something, right? It's not allowed to be infinity, which isn't really a number. So that means that in this case, there is only one correct answer. Now, when it says at what numbers is it not continuous, well, that's going to be 1, 3, and 5. And I just thought of something, and someone here hopefully has done it. Do you know when you're doing those questions where you write 3 answers, 1, 3, 5? Is WebAssign clever enough to do 5, 1, 3? Does it care that you put them in order, or it isn't really bothered? Has anybody done that yet? Where they put the numbers accidentally, right? Since you've got 5 guesses, I am going to do that. 1, 5, 3, okay? And I'm going to submit answer because this is emulating what students get. What do you mean it doesn't exist at 5? Oh, that's because I forgot to put in 1. Okay, that's fine. Yay, it will take them in any order, so you don't need to be careful about, numerical order. And this last one says, at what values of A does the overall limit exist, but f is not continuous at A? Okay, so the overall limit exists is this one. So that should be 3. Hopefully I've read it correctly. Am I good or am I good? Got it right. Now we got a, oops, that's far too big. Can't see what the heck's going on anymore. Now the next, we're still on discontinuities of various kinds, but the next question is going to deal with sketches. So they're either going to give you a description and then give you 4 pictures and you pick the one. That's the most common one. Or they get you to draw one and then you figure out what the pictures are. So it says sketch a graph of a function that is continuous except it has an infinite discontinuity at -2. Well, they really should say x equals -2, but the implication is that it is x equals -2. And a removable, what's it doing that? And a removable one at 2. So we have got 4 pictures, which you probably can't see because scale is, there we go. There are 4 pictures here. I want an infinite discontinuity at -2 and a removable one at 2. And the guy I'm picking is that one. Let's see, does that have a vertical axis, right? That's an infinite discontinuity then at -2. And do you see what a removable discontinuity at 2 looks like? Does that description match this and only this picture? There's only going to be one correct graph. In this case, that's the one. And now to be able to understand that, do you see, you need to understand what an infinite discontinuity at -2 looks like. To me, doesn't that mean a vertical asymptote at x equals -2? Now, couldn't it be a volcano one or a hole in the ground one or any of the various kinds of vertical asymptote? But that's what that means. If someone says to me a removable discontinuity, what I imagine is a continuous line with a hole in it, right? A normal line, and then they stick a hole in it. That's what a removable looks like. So can you see the normal curve and then they stuck a hole in it? Can you see the vertical asymptote? Everything matches, we are good. In this second one, we have to sketch a graph, right, that is continuous everywhere, except it has a jump discontinuity at 5 and a removable one at x equals 3. Okay, the pictures are 1, 2, 3, and the bottom one's 4, right? 1, 2, 3, and the bottom one's 4. So you are trying to find a removable one at x equals 5. Jump discontinuity at 5 and a removable one at 3.
Is it the third one again?
Okay, let's see what it looks like. Would you agree at x equals 3 that's removable? Would you agree at x equals 5 that's what we call a jump? Isn't that the 2 things that we need? You got it. Would you look, if you look at the other ones that don't work, at this one here, would you agree there's a removable at 5 and a jump at 3, but isn't that the wrong way around? Right, they should have switched places. This one has what, 2 removable, so that's not good, right? One should have been removable, one should be jump. And doesn't this last shape, doesn't it have 2 jump discontinuities, where it should have had one and the other? Okay, let's look at this fella. Oh, this is an interesting way of phrasing it. Discontinuities at 0 and 4. Right? So there's something wrong at x equals 0 and 4, but continuous from the right at 0 and continuous from the left at 4. So this graph has got a left and a right continuous going on, right? So at 0 and 4, there's a problem. At 0, it has to be continuous on the right. And at 4, it has to be continuous on the left. Which one of those pictures has all those features?
Picture 4.
Okay, so at picture 4, at x equals 0, would you agree that's continuous on the right? And at x equals 4, would you agree that's continuous on the left? And right at 0, left at 4, we nailed it. So continuous on the right, continuous on the left. Here's an example of a question. Have you noticed that almost all of these are visual in some way? Right. So there isn't any calculations or algebra or equations going on. This is our thing. Since I'm here and I'm curious, I want to see your experience. I've already got that banner I don't like. If you hit practice another, oh, they changed what's going on up here. Okay, because I was saying, hey, it's the same pictures, but I think they've changed who's left and who's right. Okay, so that's fine. Just wondered what that does. Is practice another worth it, or is it just doesn't help? Just any feedback from you? Have you used practice another? Has it been helpful?
I think practice another is helpful because if you don't understand the problem, it doesn't waste all of your attempts. But then, it's slightly different, so it doesn't.
It doesn't tell you the answer, but it gives
Yeah.
you at least a better idea of what you've been asked. That's
Yeah.
good. I've been told by other students that sometimes you know the right answer, but you don't quite know what WebAssign wants you to write the right answer as. I don't know how you phrase that, but do you know what I'm saying? Right? Do they
Yeah.
want you to just write X equals 4, or do they want you just to write 4? That kind of situation. And, because WebAssign can be very pernickety sometimes about what you do. And so they would do the try another, and it would kind of help them. Oh, they want you to write it this way, and then when they come back. So practice another is useful for that as well. I'm not going to do that one. That's pretty much the same thing. What's going on here? Oh. So in question 10, last question for today. No, not enough time. What I want to do would take too long to explain. Okay, for the last 2 minutes that we've got, put your last name down only, please.